So some molecules have some lone pairs on the central atom, and that makes things a little bit different. What we've been talking about when we talk about the arrangement of the electron groups is called the electron geometry. When there's no lone pairs, the molecular geometry is the same. The molecular geometry is the arrangement of the atoms. So here, when I've got 4 electron groups and 4 atoms, the electron geometry and the molecular geometry are the same. If there's lone pairs, they're not the same. So let's look at ammonia. Lewis structure for ammonia. Stick that in up here. There's a lone pair on the nitrogen. So we look at this Lewis structure, we say 1, 2, 3, 4 groups. 4 groups makes a tetrahedral shape. So here's our tetrahedral shape. 3 of these are bonds with hydrogen, and 1 of them is a lone pair. The lone pair is repulsive. It pushes the hydrogens away and towards each other. So it's important that we have the lone pair there, but when we talk about the shape of the molecule, we're just looking at the atoms. That's 2 teeny tiny electrons, right? Compared to the teeny tiny atoms, right? They're like 2,000 times smaller. So really small here, more than 2,000, like maybe 2 million. I don't know. Got off track. So when we look at molecular geometry, we're just looking at the atoms. So then what I like to do is say, well, let's just pretend that the lone pair is an invisible balloon. So it's there, and then it's invisible. So what do we have left? Well, we've got this shape. So what happens with my model is I look at the number of electron groups, 4 groups, tetrahedron, right? And then I'm going to pull the little ball off of one end. I still have 4 electron groups, but there's a lone pair. So this is invisible, so then I'm just describing the rest of it. So what do we call that? Well, it's a triangle, but it's not flat, right? So we call it a triangular pyramid or trigonal pyramid. Any questions? So there's that lone pair there.
So as long as there's no bond there, you don't have to focus on?
Yeah, there's no atom here.
Yeah.
So in terms of molecular geometry, we only look at the atoms.
Okay.
In terms of electron geometry, it's tetrahedral. That's looking at electron groups.
Okay.
Molecular geometry is just looking at the atoms in the molecule. You can't ignore the lone pair because then you're going to, if you just look at the atoms, you're going to say it's trigonal planar, and it isn't. It's not flat. Lone pairs are actually more repulsive. They take up more space than a single bond does because they spread out. So if we think about this, a bonding pair is stuck between two nuclei. And so it's constrained. It's sort of this fat tubular shape. A lone pair has nothing on this other end to rein it in, and so it spreads out more. So what we observe with things that have lone pairs is it messes up the angles a little bit, just like double bonds did for that trigonal planar. So this lone pair is going to take up more space, or think of it as being more repulsive. A bigger balloon is just invisible, and it's going to push these hydrogens together. So instead of 109.5, it's going to be less than that, 107. I don't need you to memorize 107 for ammonia. But if there's a lone pair, you should be able to tell me this angle is less than 109.5. Okay? Let's look at water. So water has 2 lone pairs. Again, Lewis structures are important. Because if we just say, oh, well, there's 2 hydrogens on the oxygen, that's going to be linear, right? No, it isn't. Because oxygen has 2 lone pairs. So the full Lewis structure is important to start with. So we look at the oxygen, 4 electron groups. The electron geometry is tetrahedral. But now 2 of those are lone pairs. So for the molecular geometry, we say, well, let's pretend those are invisible. So those guys are invisible. What do we have left? We got this guy left, right? So doing it with the model, 4 groups makes a tetrahedron. Pull off 2 of them. They're invisible. And what do I have left? Pull these off too. So what's the shape of that? Well, we chose this very, very fancy word. It's bent. It's not straight, it's bent, right? So some of the words are like preposterous. And then this one's so simple. This is bent. Because we have 2 lone pairs here, and they take up more space, that's going to push our atoms here, hydrogen atoms, closer together. These are going to be closer together even than in ammonia, because there's 2 lone pairs taking up space. So less than 109.5. Any questions? So relative repulsion, lone pair repulsion is the greatest. The repulsion between a lone pair and a bonding pair is intermediate, and the repulsion between 2 bonding pairs, bonding groups, like a double and a single or 2 single bonds, is the smallest. So the number of lone pairs is going to affect the bond angles. What if we have 5 electron groups and there's some lone pairs? So if we do SF4, start over and leave myself enough room. So SF4, and you got to get the right number of electrons in there. There's another pair of electrons, and those have to go on the central atom. So now what we have here is my model kit model of a trigonal bipyramid. I've got 6 groups, sorry, not 6, I've got 5 groups, 4 of them are bonds and 1's a lone pair. So I need to make one of these invisible. But these are not all the same, right? If I take this one off, if that's my lone pair, this lone pair, let me just take that guy off. If this is the lone pair, it's going to have a 90-degree angle with those guys. If I take off an equatorial, oh, I did it right the first time. Never mind. Start that over again. Rewind. Hold off the wrong one. Okay. I'm trying to do this one. So there's axial and there's equatorial. If I pull off an axial one, make that the lone pair, then it has 90-degree angles with all of these equatorial ones. You see that? All of those are 90-degree angles. If instead I make the lone pair on one of the equatorial positions, it has 90-degree angles with those 2, but with these, it's got 120. So it's got more space there. So it's going to go in the equatorial position. And that's something you got to remember. So it's going to go here instead of up there. And then what's the name of this shape? Well, it's a little easier when we actually look at the model. So, it's not a square pyramid. We call that a seesaw. Teeter totter, bread and water, wash your face in dirty water. No. They don't have these anymore at playgrounds because people got hurt. Children are going to get hurt. Anyways. Yeah, but before it was wood, it was metal with asphalt underneath. And we'd hang by our knees on the monkey bars, and people did fall and land on their heads on the asphalt. And nobody sued the school. They said, "Stupid kid, what'd you do that for?" Anyway. So this is called a seesaw. Seesaw. And if you tip it sideways, it makes more sense. So the electron geometry is bipyramidal, a trigonal bipyramid, but the molecular geometry is a seesaw. What if we have 2 lone pairs out of 5 groups? So this molecule, bromine trifluoride, has 3 bonds and 2 lone pairs. That's a total of 5 groups. Electron geometry is trigonal bipyramid, right? This shape. Again, we want to put the lone pairs in along the equator because they have more space. Because they're big and bulky, they spread out. So we're going to put them in there. So now we've got our seesaw, and we're taking off another one of those equatorial positions, and so we get this. And if you tip it 90 degrees, it looks like a T. So we call that T-shaped. Right? Xenon difluoride, we've got a total of 5 electron groups here. 2 of them are bonding pairs, and 3 of them are lone pairs. 5 groups, trigonal bipyramid again. Now we've got 3 lone pairs. Again, we're going to put the lone pairs in the equatorial positions, and now we've got this guy. And that's linear. It's the same shape as 2 electron groups, but it's got lone pairs around the middle. So invisible to 2. Okay, BF5, 6 electron groups, makes an octahedron like this. One of them is a lone pair. In the octahedral shape, all of the bond angles are the same, so it doesn't matter which one we make the lone pair. So we take that off, and you're like, well, what the heck is this? You could imagine this as a top or something, but like a faucet handle. We call that a square pyramid. Personally, I think this picture is just, you could go all kinds of places with that. I'll refrain. It takes some effort. So this is a square pyramid, because the base is a square and it comes to a point as a pyramid. Xenon tetrafluoride, putting another lone pair in here. So now we have 4 bonding pairs and 2 lone pairs. So we take this guy, and where do we want to put the other lone pair? The repulsion between lone pairs is the greatest, and so we want to put them as far away as possible, so we're going to take one on the opposite side off. So that's what we're doing here. Those are going to be opposite each other, so they have the maximum amount of space. And so we're left with this, which is square planar. So here's a table in your textbook, which is useful as a reference, showing all these different possibilities. It looks a bit overwhelming, doesn't it? If you just think about the balloons, it's not so bad. So the directions, well, here's a summary. Then we get to directions. So the geometry is determined by the number of electron groups on the central atom. And you figure that out by looking at the Lewis structure. 1 electron group is a lone pair, a single bond, a double bond, a triple bond, or a single electron. Each of those is considered 1 group. So a group is not necessarily 2 electrons. The geometry is determined by their repulsions. They're trying to get away from each other. Bond angles can vary a little bit. Multiple bonds are bulkier. Lone pairs spread out and are more repulsive. And so that'll change the bond angles a little bit. These are the instructions. Oh, wait, that's a separate section. Stop.